Silvanus Thompson. Elementary Lessons in Electricity and Magnetism. 1895. All books on my channel are in public domain. For more content like this, subscribe, like, and comment. Chapter 1. Frictional Electricity. Lesson 1. Electric Attraction and Repulsion. 1. Electricity. Electricity is the name given to an invisible agent known to us only by the effects which it produces and by various manifestations called electrical. These manifestations, at first obscure and even mysterious, are now well understood, though little is yet known of the precise nature of electricity itself. It is neither matter nor energy, yet it apparently can be associated or combined with matter, and energy can be spent in moving it. Indeed, its great importance to mankind arises from the circumstance that by its means energy spent in generating electric forces in one part of a system can be made to reappear as electric heat or light or work at some other part of the system, such transfer of energy taking place even to very great distances at an enormous speed. Electricity is apparently as indestructible as matter or as energy. It can neither be created nor destroyed, but it can be transformed in its relations to matter and to energy, and it can be moved from one place to another. In many ways its behavior resembles that of an incompressible liquid, in other ways that of a highly attenuated and weightless gas. It appears to exist distributed nearly uniformly throughout all space. Many persons, including the author, are disposed to consider it as identical with the luminiferous ether. If it be not the same thing, there is an intimate relation between the two. That this must be so, is a necessary result of the great discovery of Maxwell, the greatest scientific discovery of the 19th century, that light itself is an electric phenomenon, and that the light waves are merely electric, or, as he put it, electromagnetic waves. The name electricity is also given to that branch of science which deals with electric phenomena and theories. The phenomena, and the science which deals with them, fall under four heads. The manifestations of electricity when standing still are different from those of electricity moving or flowing along. Hence we have to consider separately the properties of statical charges, and those of currents. Further, electricity whirling round or in circulation possesses properties which were independently discovered under the name of magnetism. Lastly, electricity when in a state of rapid vibration manifests new properties not possessed in any of the previous states, and causes the propagation of waves. These four branches of the science of electricity are, however, closely connected. The object of the present work is to give the reader a general view of the main facts and their simple relations to one another. In these first lessons we begin with charges of electricity, their production by friction, by influence, and by various other means, and shall study them mainly by the manifestations of attraction and repulsion to which they give rise. After that we go on to magnetism and currents, and the relations between them. The subject of electric waves is briefly discussed at the end of the book. 2. Electric attraction. If you take a piece of sealing wax, or of resin, or a glass rod, and rub it upon a piece of flannel or silk, it will be found to have acquired a property which it did not previously possess. Namely, the power of attracting to itself such light bodies as chaff, or dust, or bits of paper, figure 1. This curious power was originally discovered to be a property of amber, or, as the Greeks called it, electroph, which is mentioned by Thales of Miletus, 600 BC. And by Theophrastus in his treatise on gems, as attracting light bodies when rubbed. Although an enormous number of substances possess this property, amber and jet were the only two in which its existence had been recognized by the ancients, or even down to so late a date as the time of Queen Elizabeth. About the year 1600, Dr. Gilbert of Colchester discovered by experiment that not only amber and jet, but a very large number of substances, such as diamond, sapphire, rock crystal, glass, sulfur, sealing wax, resin, etc., which he styled electrics, possess the same property. Ever since this time the name electricity has been employed to denote the agency at work in producing these phenomena. Gilbert also remarked that these experiments are spoiled by the presence of moisture. 3 further experiments. A better way of observing the attracting force is to employ a small ball of elder pith, or of cork, hung by a fine thread from a support. As shown in figure 2. A dry warm glass tube, excited by rubbing it briskly with a silk handkerchief, will attract the pith ball strongly, showing that it is highly electrified. The most suitable rubber, if a stick of sealing wax is used, will be found to be flannel, woolen cloth, or, best of all, fur. Boyle discovered that an electrified body is itself attracted by one that has not been electrified. This may be verified, see figure 3, by rubbing a stick of sealing wax, or a glass rod, and hanging it in a wire loop at the end of a silk thread. If, then, the hand be held out towards the suspended electrified body, the latter will turn round and approach the hand. So, again, a piece of silk ribbon, if rubbed with warm India rubber, or even if drawn between 2 pieces of warm flannel, and then hung up by one end, will be found to be attracted by objects presented to it. If held near the wall of the room, it will fly to it and stick to it. With proper precautions, it can be shown that both the rubber and the thing rubbed are in an electrified state, for both will attract like bodies. But to show this, care must be taken not to handle the rubber too much. Thus, if it is desired to show that when a piece of fur is rubbed upon sealing wax, the fur becomes also electrified, it is better not to take the fur in the hand, but to cement it to the end of a glass rod as a handle. The reason of this precaution will be explained toward the close of this lesson, and more fully in Lesson 4. A large number of substances, including iron, gold, brass, and all the metals, when held in the hand and rubbed, exhibit no sign of electrification, that is to say, do not attract like bodies as rubbed amber and rubbed glass do. Gilbert mentions also pearls, marble, agate, and the lodestone, as substances not excited electrically by rubbing them. Such bodies were, on that account, formerly termed non-electrics, but the term is erroneous, for if they are mounted on glass handles and then rubbed with silk or fur, they behave as electrics. 4. Electric repulsion. When experimenting, as in Figure 1, with a rubbed glass rod and bits of chopped paper, or straw, or bran, it will be noticed that these little bits are first attracted and fly up towards the excited rod, but that, having touched it, they are speedily repelled and fly back to the table. To show this repulsion better, let a small piece of feather or down be hung by a silk thread to a support, and let an electrified glass rod be held near it. It will dart towards the rod and stick to it, and a moment later will dart away from it, repelled by an invisible force, Figure 4, nor will it again dart towards the rod. If the experiment be repeated with another feather and a stick of sealing wax rubbed on flannel, the same effects will occur. But, if now the hand be held towards the feather, it will rush toward the hand, as the rubbed body, in Figure 3, did. This proves that the feather, though it has not itself been rubbed, possesses the property originally imparted to the rod by rubbing it. In fact, it has become electrified. By having touched an electrified body which has given part of its electricity to it, it would appear then that two bodies electrified with the same electrification repel one another. This may be confirmed by a further experiment. A rubbed glass rod, hung up as in Figure 3, is repelled by a similar rubbed glass rod, while a rubbed stick of sealing wax is repelled by a second rubbed stick of sealing wax. Another way of showing the repulsion between two similarly electrified bodies is to hang a couple of small pith balls, by thin linen threads to a glass support, as in Figure 5, and then touch them both with a rubbed glass rod. They repel one another and fly apart, instead of hanging down side by side, while the near presence of the glass rod will make them open out still wider, for now it repels them both. The self-repulsion of the parts of an electrified body is beautifully illustrated by the experiment of electrifying a soap bubble, which expands when electrified. 5. Two kinds of electrification. Electrified bodies do not, however, always repel one another. The feather which, see Figure 4, has been touched by a rubbed glass rod, and which in consequence is repelled from the rubbed glass, will be attracted if a stick of rubbed sealing wax be presented to it. And conversely, if the feather has been first electrified by touching it with the rubbed sealing wax, it will be attracted to a rubbed glass rod, though repelled by the rubbed wax. So, again, a rubbed glass rod suspended as in Figure 3 will be attracted by a rubbed piece of sealing wax, or resin, or amber, though repelled by a rubbed piece of glass. The two pith balls touched, as in Figure 5, with a rubbed glass rod fly from one another by repulsion, and, as we have seen, fly wider asunder when the excited glass rod is held near them. Yet they fall nearer together when a rubbed piece of sealing wax is held under them, being attracted by it. Symmer first observed such phenomena as these, and they were independently discovered by Dufay, who suggested in explanation of them that there were two different kinds of electricity which attracted one another while each repelled itself. The electricity produced on glass by rubbing it with silk he called vitreous electricity, supposing, though erroneously, that glass could yield no other kind. And the electricity excited in such substances as sealing wax, resin, shellac, india rubber, and amber, by rubbing them on wool or flannel, he termed resinous electricity. The kind of electricity produced is, however, found to depend not only on the thing rubbed but on the rubber also, for glass yields resinous electricity when rubbed with a cat's skin, and resin yields vitreous electricity if rubbed with a soft amalgam of tin and mercury spread on leather. Hence these names have been abandoned in favor of the more appropriate terms introduced by Franklin, who called the electricity excited upon glass by rubbing it with silk positive electricity, and that produced on resinous bodies by friction with wool or fur, negative electricity. The observations of Symmer and Dufay may therefore be stated as follows: two positively electrified bodies apparently repel one another. Two negatively electrified bodies apparently repel one another, but a positively electrified body and a negatively electrified body apparently attract one another. It is now known that these effects which appear like a repulsion and an attraction between bodies at a distance from one another are really due to actions going on in the medium between them. The positive charge does not really attract the negative charge that is near it, but both are urged toward one another by stresses in the medium in the intervening space. 6. Simultaneous production of both electrical states. Neither kind of electrification is produced alone. There is always an equal quantity of both kinds produced. One kind of period on the thing rubbed and an equal amount of the other kind on the rubber. The clearest proof that these amounts are equal can be given in some cases. For it is found that if both the minus electricity of the rubber and the plus electricity of the thing rubbed be imparted to a third body, that third body will show no electrification at all. The two equal and opposite electrifications having exactly neutralized each other. A simple experiment consists in rubbing together a disc of sealing wax and one covered with flannel, both being held by insulating handles. To test them is required an insulated pot and an electroscope, as in figure 29. If either disc be inserted in the pot, the leaves of the electroscope will diverge. But if both are inserted at the same time, the leaves do not diverge, showing that the two charges on the discs are equal and of opposite sign. In the following list, the bodies are arranged in such an order that if any two be rubbed together, the one which stands earlier in the series becomes positively electrified, and the one that stands later negatively electrified. Fur, wool, ivory, glass, silk, metals, sulfur, India rubber, gutta-percha, collodion, or celluloid. 7. Theories of electricity. Several theories have been advanced to account for these phenomena, but all are more or less unsatisfactory. Symmer proposed a two-fluid theory, according to which there are two imponderable electric fluids of opposite kinds, which neutralize one another when they combine, and which exist combined in equal quantities in all bodies until their condition is disturbed by friction. A modification of this theory was made by Franklin, who proposed instead a one-fluid theory, according to which there is a single electric fluid distributed usually uniformly in all bodies, but which, when they are subjected to friction, distributes itself unequally between the rubber and the thing rubbed, one having more of the fluid, the other less, than the average. Hence the terms positive and negative, which are still retained. That body which is supposed to have an excess being said to be charged with positive electricity, usually denoted by the plus sign, while that which is supposed to have less is said to be charged with negative electricity and is denoted by the minus sign. These terms are, however, purely arbitrary, for in the present state of science we do not know which of these two states really means more and which means less. In many ways electricity behaves as a weightless substance, as incompressible as any material liquid. It is, however, quite certain that electricity is not a material fluid, whatever else it may be. For while it resembles a fluid in its property of apparently flowing from one point to another, it differs from every known fluid in almost every other respect. It possesses no weight, it repels itself. It is, moreover, quite impossible to conceive of two fluids whose properties should in every respect be the precise opposites of one another. For these reasons it is clearly misleading to speak of an electric fluid or fluids, however convenient the term may seem to be. In metals and other good conductors electricity can apparently move and flow quite easily in currents. In transparent solids, such as glass and resin, and in many transparent liquids such as oils, and in gases such as the air, if still, and not rarefied, electricity apparently cannot flow. Even a vacuum appears to be a non-conductor. In the case of all non-conductors electricity can only be moved by an action known as displacement, see Article 67. It appears then that in metals electricity can easily pass from molecule to molecule. But in the case of non-conductors the electricity is in some way stuck to the molecules, or associated with them. Some electricians, notably Faraday, have propounded a molecular theory of electricity, according to which the electrical states are the result of certain peculiar conditions of the molecules of the surfaces that have been rubbed. Another view is to regard the state of electrification as related to the ether, the highly attenuated medium which fills all space, and is the vehicle by which light is transmitted, which is known to be associated with the molecules of matter. Some indeed hold that the ether itself is electricity, and that the two states of positive and negative electrification are simply due to displacement of the ether at the surfaces of bodies. In these lessons we shall avoid as far as possible all theories, and shall be content to use the term electricity. 8. Charge. The quantity of electrification of either kind produced by friction or other means upon the surface of a body is spoken of as a charge, and a body when electrified is said to be charged. It is clear that there may be charges of different values as well as of either kind. When the charge of electricity is removed from a charged body, it is said to be discharged. Good conductors of electricity are instantaneously discharged if touched by the hand or by any conductor in contact with the ground, the charge thus finding a means of escaping to earth or to surrounding walls. A body that is not a good conductor may be readily discharged by passing it rapidly through the flame of a spirit lamp or a candle. For the hot gases instantly carry off the charge and dissipate it in the air. Electricity may either reside upon the surface of bodies as a charge, or flow through their substance as a current. That branch of the science which treats of the laws of the charges, that is to say, of electricity at rest, upon the surface of bodies is termed electrostatics, and is dealt with in Chapter 4. The branch of the subject which treats of the flow of electricity in currents is dealt with in Chapter 3, and other later portions of this book. 9. Modes of representing electrification. Several modes are used to represent the electrification of surfaces. In figures 6 and 7 and 8 are represented two discs, A covered with woolen cloth, B of some resinous body, which have been rubbed together so that it has become negatively electrified. Figure 6 the surfaces are marked with plus and minus signs. In figure 7 dotted lines are drawn just outside the positively electrified surface and just within the negatively electrified surface, as though one had a surplus and the other a deficit of electricity. In figure 8 lines are drawn across the intervening space from the positively electrified surface to the opposite negative charge. The advantages of this last mode are explained in Article 13. 10. Conductors and insulators. The term conductors, used above, is applied to those bodies which readily allow electricity to flow through them. Roughly speaking, bodies may be divided into two classes, those which conduct and those which do not. Though very many substances are partial conductors, and cannot well be classed in either category. All the metals conduct well, the human body conducts, and so does water. On the other hand, glass, sealing wax, silk, shellac, gutta-percha, India rubber, resin, fatty substances generally, and the air, are non-conductors. On this account, these substances are used to make supports and handles for electrical apparatus where it is important that the electricity should not leak away. Hence they are sometimes called insulators or isolators. Faraday termed them dielectrics. We have remarked above that the name of non-electric was given to those substances which, like the metals, yield no sign of electrification when held into a hand and rubbed. We now know the reason why they show no electrification. For, being good conductors, the electrification flows away as fast as it is generated. The observation of Gilbert that electrical experiments fail in damp weather is also explained by the knowledge that water is a conductor. The film of moisture on the surface of damp bodies causing the electricity produced by friction to leak away as fast as it is generated. 11. Other electrical effects. The production of electricity by friction is attested by other effects than those of attraction and repulsion, which hitherto we have assumed to be the test of the presence of electricity. Otto von Guericke first observed that sparks and flashes of light could be obtained from highly electrified bodies at the moment when they were discharged. Such sparks are usually accompanied by a snapping sound, suggesting on a small scale the thunder accompanying the lightning spark, as was remarked by Newton and other early observers. Pale flashes of light are also produced by the discharge of electricity through tubes partially exhausted of air by the air pump. Other effects will be noticed in due course. 12. Other sources of electrification. The student must be reminded that friction is by no means the only source of electrification. The other sources, percussion, compression, heat, chemical action, physiological action, contact of metals, etc., will be treated of in Lesson 7. We will simply remark here that friction between two different substances always produces electrical separation, no matter what the substances may be. Symmer observed the production of electrification when a silk stocking was drawn over a woolen one, though woolen rubbed upon woolen, or silk rubbed upon silk, produces no electrical effect. If, however, a piece of rough glass be rubbed on a piece of smooth glass, electrification is observed. And indeed the conditions of the surface play a very important part in the production of electrification by friction. In general, of two bodies thus rubbed together, that one becomes negatively electrical whose particles are the more easily removed by friction. Differences of temperature also affect the electrical conditions of bodies, a warm body being usually negative when rubbed on a cold piece of the same substance. The quantity of electrification produced is, however, not proportional to the amount of the actual mechanical friction. Hence it appears doubtful whether friction is truly the cause of the electrification. Something certainly happens when the surfaces of two different substances are brought into intimate contact, which has the result that when they are drawn apart they are found, provided at least one of them is a non-conductor, to have acquired opposite charges of electrification. One surface having apparently taken some electricity from the other. But these opposite charges attract one another and cannot be drawn apart without there being mechanical work done upon the system. The work thus spent is stored up in the act of separating the charged surfaces, and as long as the charges remain separated they constitute a store of potential energy. The so-called frictional electric machines are therefore machines for bringing dissimilar substances into intimate contact, and then drawing apart the particles that have touched one another and become electrical. If the two bodies that are rubbed together are both good conductors, they will not become strongly electrified, even if held on insulating handles. It is quite likely, however, that the heat produced by friction, as in the bearings of machinery, is due to electric currents generated where the surfaces meet and slip. 13. Electric field. Whenever two oppositely charged surfaces are placed near one another they tend to move together, and the space between them is found to be thrown into a peculiar state of stress, as though the medium in between had been stretched. To explore the space between two bodies, one of which has been positively and the other negatively electrified, we may use a light pointer, figure 9, made of a small piece of very thin paper pierced with a hole through which passes a long thread of glass. It will be found that this pointer tends to point across from the positively electrified surface to the negatively electrified surface, along invisible lines of electric force. The space so filled with electric lines of force is called an electric field. In Figure 8a and b represent two bodies the surfaces of which have been electrified, the one positively, the other negatively. In the field between them the electric lines pass across almost straight, except near the edges, where they are curved. Electric lines of force start from a positively charged surface at one end, and end on a negatively charged surface at the other end. They never meet or cross one another. Their direction indicates that of the resultant electric force at every point through which they pass. The stress in the medium thus mapped out by the lines of force acts as a tension along them, as though they tended to shorten themselves. In fact, in Figure 8 the tension in the medium draws the two surfaces together. There is also a pressure in the medium at right angles to the lines, tending to widen the distance between them. Figure 10 represents a ball which has been positively electrified and placed at a distance from other objects, the lines in the field being simply radial. Lesson 2. Electroscopes. 14. Simple electroscopes. An instrument for detecting whether a body is electrified or not, and whether the electrification is positive or negative, is termed an electroscope. The feather which was attracted or repelled, and the two pith balls which flew apart, as we found in Lesson I, are in reality simple electroscopes. There are, however, a number of pieces of apparatus better adapted for this particular purpose, some of which we will describe. 15. Needle electroscope. The earliest electroscope was devised by Dr. Gilbert, and shown in Figure 11, which consists of a stiff strip balanced lightly upon a sharp point. A thin strip of brass or wood, a straw, or even a goose quill, balanced upon a sewing needle, will serve equally well. When an electrified body is held near the electroscope it is attracted and turned round, and will thus indicate the presence of electric charges far too feeble to attract bits of paper from a table. 16. Gold leaf electroscope. A still more sensitive instrument is the gold leaf electroscope, invented by Bennett, and shown in Figure 12. We have seen how two pith balls when similarly electrified repel one another and stand apart, gravity being partly overcome by force of the electric repulsion. A couple of narrow strips of the thinnest tissue paper, hung upon a support, will behave similarly when electrified. But the best results are obtained with two strips of gold leaf, which, being excessively thin, is much tighter than the thinnest paper. The gold leaf electroscope conveniently made by suspending the two leaves with a wide-mouthed glass jar, which both serves to protect them from draughts of air and to support them from contact with the ground. The mouth of the jar should be closed by a plug of paraffin wax, through which is pushed a bit of varnished glass tube. Through this passed a stiff brass wire, the lower end of which is bent at a right angle to receive the two strips of gold leaf, while the upper supports a flat plate of metal, or may be furnished with a brass knob. When kept dry and free from dust it will indicate excessively small quantities of electrification. A rubbed glass rod, even while 2 or 3 feet from the instrument, will cause the leaves to repel one another. The chips produced by sharpening a pencil, falling on the electroscope top, are seen to be electrified. If the knob be even brushed with a small camel's hairbrush, the slight frictions produces a perceptible effect. With this instrument all kinds of friction can be shown to produce electrification. Let a person, standing upon an insulating support, such as a stool with glass legs, or a board supported on 4 glass tumblers, be briskly struck with a silk handkerchief, with fox's tail, or even brushed with a clother's brush, he will be electrified, as will be indicated by the electroscope if he place one hand on the knob at the top of it. The gold leaf electroscope can further be used to indicate the kind of electrification on an excited body. Thus, suppose we rubbed a piece of brown paper with a piece of India rubber and desired to find out whether the electrification on the paper was plus or minus, we should proceed as follows. First charge the gold leaves of the electroscope by touching the knob with a glass rod rubbed on silk. The leaves diverge, being electrified with plus electrification. When they are thus charged the approach of a body which is positively electrified will cause them to diverge still more widely, while, on the approach of one negatively electrified, they will tend to close together. If now the brown paper be brought near the electroscope, the leaves will be seen to diverge more, proving the electrification of the paper to be of the same kind as that with which the electroscope is charged, or positive. Sometimes the outer surface of the glass jar containing the gold leaves is covered with wire gauze or strips of foil to shield the leaves from the influence of external bodies. A preferable way is to use glass of a kind that conducts. The part played by the surrounding medium in the operation of the electroscope is illustrated by Figure 13. Of the electric lines in the field surrounding the rubbed rod a number will pass into the metal cap of the electroscope and emerge below through the leaves. The nearer the rod is brought, the greater will be the number of electric lines thus affecting the instrument. There being a tension along the lines and a pressure across them, the effect is to draw the gold leaves apart as though they repelled each other. The gold leaf electroscope will also indicate roughly the amount of electrification on a body placed in contact with it. For the gold leaves open out more widely when the charge thus imparted to them is greater. For exact measurement, however, of the degree of electrification, recourse must be had to the instruments known as electrometers, described in Lesson 12. In another form of electroscope Bohnenberg's, a single gold leaf is used, and is suspended between two metallic plates, one of which can be positively, the other negatively electrified, by placing them in communication with the poles of a dry pile. If the gold leaf be charged positively or negatively, it will be attracted to one side and repelled from the other, according to the law of attraction and repulsion mentioned in Article 4. Henle's semaphore. As an indicator for large charges of electricity, there is sometimes used a semaphore like that shown in Figure 14. It consists of a pith ball at the end of a light arm fixed on a pivot to an upright. When the whole is electrified, the pith ball is repelled from the upright and flies out at an angle, indicated on a graduated scale or dial behind it. This little electroscope, which is seldom used except to show whether an electric machine or a Leyden jar is charged, must on no account be confused with the delicate quadrant electrometer described in Lesson 12, whose object is to measure very small charges of electricity, not to indicate large ones. 18. The torsion balance. Although more properly an electrometer than a mere electroscope, it will be most convenient to describe here the instrument known as torsion balance Figure 15. This instrument, once famous, but not obsolete, served to measure the force of repulsion between two similarly electrified bodies. By balancing the repelling force against the force exerted by a fine wire in twisting itself after it had been twisted. The torsion balance consists of a light arm or lever of shellac suspended within a cylindrical glass case by means of a fine silver wire. At one end, this lever is furnished with a gilt pith ball N. The upper end of the silver wire is fastened to a brass top, upon which a circle, divided into degrees, is cut. This top can be turned round in the tube which supports it, and is called the torsion head. Through an aperture in the cover there can be introduced a second gilt pith ball M, fixed to the end of a vertical glass rod A. Round the glass case, at the level of the pith balls, a circle is drawn, and divided also into degrees. In using the torsion balance to measure the amount of a charge of electricity, the following method is adopted. First, the torsion head is turned round until the two pith balls M and N just touch one another. Then the glass rod, A, is taken out, and the charge of electricity to be measured is imparted to the ball M, which is then replaced in the balance. As soon as M and N touch one another, part of the charge passes from M to N, and they repel one another because they are then similarly electrified. The ball N, therefore, is driven round and twists the wire up to a certain extent. The force of repulsion becomes less and less as N gets farther and farther from M, but the force of the twist gets greater and greater the more the wire is twisted. Hence these two forces will balance one another when the balls are separated by a certain distance. And it is clear that a large charge of electricity will repel the ball N with a greater force than a lesser charge would. The distance through which the ball is repelled is read off in angular degrees of the scale. When a wire is twisted, the force with which it tends to untwist is precisely proportional to the amount of the twist. The force required to twist the wire 10 degrees is just 10 times as great as the force required to twist it 1 degree. In other words, the force of torsion is proportional to the angle of torsion. The angular distance between the two balls is, when they are not very widely separated, very nearly proportional to the actual straight distance between them, and represents the force exerted between electrified balls at that distance apart. The student must, however, carefully distinguish between the measurement of the force and the measurement of the actual quantity of electricity with which the instrument is charged. For the force exerted between the electrified balls will vary at different distances according to a particular law known as the law of inverse squares, which requires to be carefully explained. 19. The law of inverse squares. Coulomb proved, by means of the torsion balance, that the force exerted between two small electrified bodies varies inversely as the square of the distance between them when the distance is varied. Thus, suppose two small electrified bodies 1 inch apart repel one another with a certain force. At a distance of 2 inches the force will be found to be only 1/4 as great as the force at 1 inch, and at 10 inches it will be only 1/100th part as great as at 1 inch. This law is proved by the following experiment with the torsion balance. The two scales were adjusted to 0 degrees, and a certain charge was then imparted to the balls. The ball N was repelled round to a distance of 36 degrees. The twist on the wire between its upper and lower ends was also 36 degrees, or the force tending to repel was 36 times as great as the force required to twist the wire by 1 degree. The torsion head was now turned round so as to twist the thread at the top and force the ball N nearer to M, and was turned round until the distance between N and M was halved. To bring down this distance from 36 degrees to 18 degrees, it was found needful to twist the torsion head through 126 degrees. The total twist between the upper and lower ends of the wire was now 120 degrees plus 18 degrees, or 144 degrees. And the force was 144 times as great as that force which would twist the wire 1 degree. but 144 is 4 times as great as 36. Hence we see that while the distance had been reduced to 1/2, the force between the balls had become 4 times as great. Had we reduced the distance to 1/4, or 9 degrees, the total torsion would have been found to be 576 degrees, or 16 times as great, proving the force to vary inversely as the square of the distance. In practice, it requires great experience and skill to obtain results as exact as this, for there are many sources of inaccuracy in the instrument. The balls must be very small, in proportion to the distances between them. The charges of electricity on the balls are found, moreover, to become gradually less and less, as if the electricity leaked away into the air. This loss is less if the apparatus be quite dry. It is therefore usual to dry the interior by placing inside the case a cup containing either chloride of calcium, or pumice stone soaked with strong sulfuric acid, to absorb the moisture. Before leaving the subject of electric forces, it may be well to mention that the force of attraction between two oppositely electrified bodies varies also inversely as the square of the distance between them. And in every case, whether of attraction or repulsion, the force at any given distance is proportional to the product of the two quantities of electricity on the bodies. Thus, if we had separately given a charge of 2 to the ball M and a charge of 3 to the ball N, the force between them will be 3 times 2 equals 6 times as great as if each had had a charge of 1 given to it. It must be remembered, however, that the law of inverse squares is only true when applied to the case of bodies so small, as compared with the distance between them, that they are mere points. For flat, large, or elongated bodies the law of inverse squares does not hold good. The attraction between two large flat disks oppositely electrified with given charges, and placed near together, does not vary with the distance. 20. Field between two balls. The electric field, described in Article 13, between two oppositely electrified balls is found to consist of curved lines. By the principle laid down in Article 13, there is a tension along these lines so that they tend not only to draw the two balls together, but also to draw the electrifications on the surfaces of the balls toward one another. There is also a lateral pressure in the medium tending to keep the electric lines apart from one another. One result of these actions is that the charges are no longer equally distributed over the surfaces, but are more dense on the parts that approach most nearly. 21. Unit quantity of electricity. In consequence of these laws of attraction and repulsion, it is found most convenient to adopt the following definition for that quantity of electricity which we take. For a unit or standard by which to measure other quantities of electricity. 1. Electrostatic. Unit of electricity is that quantity which, when placed at a distance of 1 centimeter in air from a similar and equal quantity, repels it with a force of 1 dyne. If instead of air another medium occupies the space, the force will be different. For example, if petroleum is used, the force exerted between given charges will be about half as great, Article 50. Further information about the measurement of electrical quantities is given in lessons 21 and 22.